Hi, I'm going to tell you about how to compute power series composition in near-linear time. This is Baitian, and the presentation is based on a joint work with Yasunori. First, what is the power series composition problem? A fundamental question in computer algebra is to support basic operations over power series. The power series can be regarded as a polynomial with infinitely many terms. Since we cannot store infinite information in computer, we only care about the coefficients up to a certain degree. This can be seen as an analogy of the finite precision of a real number. So, there are several basic operations. For the sum of two power series, you can just add the coefficients pointwisely. So this is a trivial linear time algorithm. For the product of two power series, the new coefficient sequence is the convolution of the two sequences. The fast Fourier transform algorithm can yield a near linear time algorithm to compute the product of two power series. And then we come to the composition problem. So here is an example of the power series composition. You just plug in x with g and then expand the terms according to the basic arithmetic rules. And the power series composition problems also has several applications in combinatorics and cryptography. What are the known results of this problem? First, let me talk about some near-linear time algorithms for special cases. I want to remark that in our video, near-linear times always means n times polylog n. First, I want to define a function mn denoting the time computing the product of two polynomials. The specific value of mn may vary due to the mode of computation or the coefficient rings, but it's always a near-linear time. When f is algebraic, the composition can be computed in OMN time. When G is algebraic or has some other structures, the composition problem can be computed only with a logarithmic overhead. I want to remark that both these two class of algorithms are algebraic algorithms, in the sense that they only use field operations. And there are some progress on the general cases. There's a textbook algorithm that computes the power series composition in n to the 1.5 time, and this is also an algebraic algorithm. There's a breakthrough by Kelaya and Humans. They show that if the coefficient ring is a finite field, they gave two algorithms. The first one runs in almost linear time, but it's not an algebraic algorithm. It only works on Turing machines or RAM models, etc. The second one is an almost linear time algorithm, but it depends on the characteristic of the field. And there is another result by Nager, Salvi, Scholz, and Villard. They show that the composition also admits an algebraic algorithm runs in n to the kappa time. Here kappa is a number depending on the matrix multiplication exponent and the rectangular matrix multiplication exponent. And I want to remark that these two algorithms, they not only works for the power series composition problem, they actually works for more generalized class of problems called modular composition problems. So you also have a polynomial h and you want to compute f compose g mod h. So the power series composition problem is just the special case that takes h to the power of x. The main result of this work is to propose a near-linear time algebraic algorithm for power series composition. More precisely, it runs in OMN log n time, which matches some known special cases known before, but the technique is entirely different. we want to remark that this is also faster than the Cadillac-Humans algorithm, even in the Turing machine model, because their almost linear time algorithm seems to have a super polylog factor. And I want to remark that our algorithm is also both simple and algebraic. Our strategy is as follows. We didn't solve the power series composition problem directly. In contrast, we first solved the problem called power projection problem in the same time. And that problem is actually a transpose problem, or so-called dual problem of the power series composition. And then, by a general principle called transposition principle in computer algebra, we obtain an algorithm for the power series composition. First, let me introduce the transposition principle. It says that if you have an algorithm that computes the linear transform x to a times x, so here x is a vector and a is a matrix, then the transposed problem defined by y times y to a transpose times y. This problem can be computed in the same complexity. Okay, so actually this principle has a very simple proof of it. So it really depends on the fact that your algorithm is algebraic. So you can write your algorithm as a circuit. So the input gates are x and the output gates, we call them y. And there are some numbers writing on each wire. And your algebraic algorithm can always be represented in this way, such that each gate is the linear combination of its input gates. And then how you obtain the transposed problem. So this picture already shows how to do that. So you can just reverse each of the wires, and then each output gate now becomes an input gate, and the input gate becomes an output gate. And you can check that this circuit just computes the transposed matrix. Okay, so how can we write down a linear problem of the power series composition? We write the vector u as the coefficient of our power series F. And we write matrix A with the coefficients of the power of gxi. Then this linear problem can be written as follows. Okay, so let's look about the transpose problem of this linear transform. So note that we can just swap the positions of the ui and vj and change the summation subscript from I to j. So this is the transpose problem. Okay, so this problem is called power projection because for each ui, you're computing the linear combination of the coefficient of gx to the ith power with a certain vector. The next step is a reduction. We're going to reduce the power projection problem to a quotient of certain kind of power series. The equations of this slide may all look like playing with symbols, but we will figure out what happens in the next few slides. First, we are going to turn the inner product into a coefficient extraction. So we define the polynomial px in the following form, and then we can rewrite the inner product as the extraction of the product px times gx to the ith power. Then we are going to write down the generating function of sequence ui. So we just multiply with y to the ith power on both sides and take summation. The left-hand side is the generating function of ui, and the right-hand side is px divided by 1 minus y times gx. Okay, so this is a quotient problem. But now we introduced a new variable. So we're going to figure out what happens later. So how to compute the quotient of two-power series? There are basically two ways to do this. The first way is called the Newton iteration, and the second way is called the Grave iteration. Both of these two methods originate from numerical algorithms, but then people found its analogy in power series arithmetic. The Newton iteration is quite useful. It is then generalized to computing square root f, exponential of f, and any algebraic function composing with f. And this method is also quite practical. There are massively following works on improving the constant factors of Newton iteration. However, the Grave iteration is somehow attracting a little attention during about 20 years, until a recent SOSA paper by Boston and Mori. They used the Grave iteration to propose a new algorithm to evaluate a linear recurrent sequence. And this iteration is also the key ingredient of our algorithm. So how did the Grave iteration algorithm works? So now we are considering the problem of computing the nth coefficient of a quotient p divided by q. For simplicity, we just assume that n equals to a power of 2. Otherwise, we can do padding on p. So this is as follows. Well, actually the Grave iteration can be explained in only one sentence. It is just the following trick. Consider multiplying both the numerator and the denominator with q minus x. Then, when you look at the denominator, it doesn't have the odd degree terms. And then you can also split the numerator with its odd part and even part. Since you're extracting the nth coefficient, so suppose n is not 1, and when n is a power of 2, n must be an even number. Then you could reduce the problem to a subproblem with n becomes n divided by 2. And then you do this over and over again. Each time you pay the multiplication time to compute P0 and Q0 from P and Q. And the overall time is still OMN. Okay, so the overall process of the Grave iteration is pictured as follows. It have log n phases in total, and each time the n is half by half. However, this OMN time complexity measures the ring operations number. But in our application, we take the coefficient ring as AY, so there is an intermediate Y here. But we want to measure the total arithmetic operations over the coefficient ring A. So we need to take a closer look at our algorithm. Okay, let's see what happened on this polynomial ring. So let's first check the initial conditions of the P0 and Q0. We know that P0 is a polynomial in X, and Q0 is 1 minus y times gx. So it is a polynomial that has y degree 1. And note that in each iteration, this qi and pi comes from the product of two polynomials, so its y degree just doubles. However, its x degree gets halved. So in each time, we pay the time on multiplying two polynomials of x degree n divided by 2k and y degree 2 to k. And there is a basic trick in polynomial arithmetic called Kronecker substitution. We can do this multiplication in OMN time. And since there are only log n rounds, the total time complexity is just OMN log n. Okay, that's done. So let us get to the conclusion. We have obtained a quite simple and algebraic algorithm to compute the power projection problem. And then, by transposition principle, we can rewrite the above algorithm to an algorithm computing the power series composition. And if you are interested in the explicit description of this transposed algorithm, you can check our paper. Finally, there are some open questions. So, can our algorithm be generalized to compute the modular composition problem? Or can we find an algebraic algorithm that computes modular composition in almost linear time? Or can we compute modular composition in near linear time for at least some special cases like the field is a finite field? That's all of this video. Thanks for listening.